Hi, my name is Marco Wurps. I'm currently doing a master's degree in computer engineering at, I'm currently doing a master's degree in computer engineering at the Leibniz University Hannover. And next to my studies, I work as a student worker in the field application engineering department at BlackBerry QNX. And today I want to talk to you about the BlackBerry QNX Academy for Functional Safety. So first of all, I want to give you a very short introduction to functional safety. So talk really about a few core things to have in mind. Then I want to introduce you to our BlackBerry QNX Academy. And finally, I want to show you one of our pre-built demos live here with the robot that I have with me. I don't know if you can see it from the back, but we'll see it later on during the live part. So, first of all, what does functional safety even mean? And I want to start by sharing a definition from TÜV Süd with you. And that definition is systems that lead to the freedom from unacceptable risk of injury or damage to the health of people by the proper implementation of one or more automatic protection functions. And if we really look at this definition, we can see that functional safety is really all about protecting users from technology by employing an active automatic secondary functional safety system, or protecting users from technology by actively employing technology ourselves. And what's really important to know about functional safety is that there are multiple functional safety standards that may be relevant to you depending on the industry that you're in. For example, if you're doing automotive applications, then the functional safety standard ISO 26262 may apply to you. Or if you're doing industrial applications, then IEC 61508 may be relevant to you. And then, if you're trying to get certified against a certain standard, then you, of course, need during your design phase, you need to follow all of your functional safety standards requirements. So you need to have a look at your functional safety standards, and you really have to see what requirements are there, and then you need to fulfill them in your design. Later on, you need to prepare what's called a safety case. So a safety case is a structured argument as to why a software is safe from a functional safety point of view. And in the end, you can get your design certified against the standard. And just from this very basic introduction, we can see that functional safety is actually a really important topic, because when you work in an industry that requires you to follow such a functional safety standard, then naturally functional safety will become really important to you. And now I want to introduce you to an example, or a thought experiment maybe. So let's say we want to develop software for an industrial robot system that's supposed to be working on parts at an assembly line using a computer vision algorithm to detect and slightly adjust its motion according to how the parts are laid out in space. So let's say we want to have 3 different software components. So we want to have a vision component, a motion component, and a cloud component. So my vision component should just use my computer vision algorithm to detect how the parts are laid out in space. My motion component should take the results from my vision component and update the motion planning of my robot accordingly. And then we have a third, rather unrelated cloud component, which should just send some diagnostics data to a cloud service. And we have one more requirement. We want all of this to run on one system on chip, because we want to reduce hardware complexity and hardware cost. And let's also say that during our design phase, we have determined that our vision and our motion component are safety critical. So I won't get too much into detail about how to do this or the specifics of this, but it's important to know that the more safety critical your component is, the higher the stricter the requirements are that your functional safety standard will set out for you as to mitigate the safety risks that these components pose, basically. And now, if we really look at this example, we can see that we have safety-critical components, we have non-safety-critical components, and we want to run them on one computational platform. And because of this, we have what is called a mixed criticality system. And now we want to have a look at the functional safety standard IEC 61508 to really see what a requirement from a functional safety standard might look like. And now, if we have a look at this functional safety standard, we can see that it says about our example, or about mixed criticality systems in general, that components that run on the same computational platform need to comply with the safety criticality of our most critical component. So for our example, this means that our cloud component, which is we have determined is non-safety critical, would need to be developed to the same higher, more difficult to achieve requirements as my vision and my motion component. And you can see that for us, this would mean that we have to spend additional time, additional effort during our design phase. And if we think about an example with more components, we can really see that we want to avoid this. And to avoid this, we need to demonstrate what is called freedom from interference. So freedom from interference can be split up, among other things, into spatial independence and temporal independence. So spatial independence means that one component should not be able to change to corrupt the data of another component, as to avoid the scenario which I've shown you on the left, where app2 destroys the memory of app1. And temporal independence means that one component should not cause another component to fail by taking too high a share of the available processing time. As to avoid the scenario which I've shown you on the right, where app1 must run regularly, but suddenly can't because app2 takes too much time. And this is really all about ensuring that my components, which have not been developed to my most strictest requirements, can't indirectly interfere with my most critical component and cause them to fail, basically. So now we know that we want to have freedom from interference, but how can we actually achieve this? And one way to achieve this is to use a real-time operating system. So you can see now in the figure that we have used a real-time operating system to enforce these spatial and temporal independence properties for us. And we can run our vision, our motion, and our cloud component on top of that. But we also need to consider that this real-time operating system now becomes part of our software stack of the safety case that we need to prepare. And then in the end, we need to certify our software, and our RTOS is now really part of that. And that's generally easier when using a pre-certified RTOS. So an RTOS that is pre-certified to the functional safety standard that I'm trying to certify against, like the QNX OS for safety or the QNX hypervisor for safety, which are both at the highest level pre-certified to functional safety standards in the domains of automotive, medical, and industrial applications. But now you might wonder, okay, well, how does QNX actually achieve these spatial and temporal independence properties? And so first of all, for spatial independence, it's important to know that QNX has what is called a microkernel architecture. So this means that many OS components are run as standard processes in user space. So this also means that they have their own address spaces, and they can make use of memory management units to really enforce this address space protection mechanisms. Then it's important to know that with our hypervisor, we can run guests on our guests as virtual machines. And then we can have freedom from interference between guest and host operation. Also, we need to think about bus mastering devices. So, for example, DMA devices, because they can copy things around in memory and therefore potentially corrupt safety-critical memory areas. And as to avoid this, we have integrated MMU support, so that we can control which memory areas a DMA device can or cannot access. And finally, for temporal separation, we have what is called an adaptive partitioning scheduler. So using this adaptive partitioning scheduler, we can create a partition, let's say a 30% partition, and I can place my critical component in this 30% partition, and then I'm always ensured that it will get 30% of the CPU time. So even if I have another partition and my network stack is in there, let's say, and it's getting bombarded with requests, I'm always ensured that my critical component in its 30% partition will get 30% of the CPU time. Okay, so this already concludes the first part of my presentation. So with this very short introduction to functional safety, we have seen why it is such an important topic. And because it is such an important topic, BlackBerry QNX and Texas Instruments have collaborated to create the BlackBerry QNX Academy for Functional Safety. So this is a free introductory course about functional safety. So you can look at learning materials there to really learn about the basics of functional safety. But not only that, you can also try out some practical demos to get some practical hands-on experience with functional safety that way. And to be a bit more specific about what we are offering with this BlackBerry QNX Academy for Functional Safety. So we are offering self-paced learning materials that were created by functional safety experts from BlackBerry QNX. And there you can learn about preparing and structuring safety cases, which I've mentioned earlier. You can learn about minimizing faults, errors, and failures, and many more topics. You can get free 90-day evaluation licenses for the QNX software development platform, the QNX OS for safety, the QNX hypervisor for safety. We provide you with instructions on how to acquire the hardware needed to actually build the demo robot that I have with me here on stage. And we also provide you with a pre-built image for the embedded board of the robot, which contains multiple demos. For example, a startup verifier and fault injector demo. And so using the startup verifier, you can verify after the boot process that important hardware registers are configured correctly so that the system is in a known state before our QNX operating system starts. And then we have an object detection and ranging demo. I'll show you that in a minute. We also have a subject follower demo where our robot can actually follow a moving object around. And we also have a LiDAR-based navigation demo. And these demos are really easy to use. You just have to flash them to an SD card, plug this SD card into the embedded board of your robot, and then you can try them out. But you can also modify them later on and get your practical experience with functional safety that way. Okay, now I want to switch to the live part. We just set this up really quick. Yeah, so this is our object detection and ranging demo. So first of all, it's important to note that all the computation is happening on the embedded board inside of this robot. Just the visualization that you can see here is happening on a development PC. And on the upper left, you can see the object detection part of this demo. Here we are running inference on our embedded board and use a deep learning algorithm to categorize different objects. For example, we can see here that it's detecting a few persons. On the lower left, you can see the ranging part of this demo. So here we use 2 cameras to calculate for every pixel how far it is away from the camera. And if it's closer to the camera, we color it red. And if it's further away, we color it blue. On the right, you can see a point cloud. So this is really a top-down view, and you can see for a few select points how far, again, they are away from the camera. So this is also part of our ranging demo. And there's also this heartbeat panel. So we are also running a QNX guest on top of our hypervisor. And this has a heartbeat component, and it sends for every second a heartbeat. And here you can see this has been running for almost 9,000 seconds. And I could actually kill this guest and then see it restart. And what's important about this is that all of the other computation or the visualization wouldn't be affected by this. We could show this if I would kill the guest. Yeah, and finally, I want to go a bit more into detail about the software stack of this demo. So let me switch back to my presentation. Okay. Okay, so all of this is running on the TI Edge AI starter board, which has built-in hardware accelerators for real-time computer vision algorithms, and it uses the TDA4VM processor. On top of that, as our foundational software, which is pre-certified to the functional safety standards, we run our QNX hypervisor for safety. On top of that, we run ROS2. So if you're not familiar with ROS2, ROS2 is a very popular middleware that is used in robotics. It offers lots of common functionalities to robotics applications. It has the concept of nodes, which can execute on top of it. And it offers these nodes basically a communication framework so that they can easily exchange messages. And really, these ROS2 nodes are what do most of the work. So for example, we have a TI SDE node, which is doing the stereo depth estimation, so the ranging part of the demo we've just seen. Or the TI Vision CNN node is, together with other nodes, doing the object detection part of this demo. And what's really important about this is that these nodes are not something that we've developed from the ground up, but we have taken them from the TI Robotics SDK for Linux, and we have ported this to the QNX operating system. And we also have, as I've mentioned during our live demo, we have a QNX guest, which is also ROS2 running, and then our heartbeat component on top of that. And we've also ported not only the TI Robotics SDK, but also its dependencies, for example, the TI TensorFlow Lite library. And these nodes actually really make use of the TDA4VM's built-in hardware accelerators internally. So what's important if we look at this example is that we can really do such a complex computer vision or machine learning application while still using a real-time operating system, which is already pre-certified to functional safety standards. So we can really do such a complex application while still putting an emphasis on functional safety from the beginning, as we've really seen with this demo. And yeah, that's already the end of my presentation. So thank you very much for attending. If you're interested, I have a QR code which you can scan. This will take you to the page of our BlackBerry QNX Academy. You can check that out if you'd like. And now you can ask questions, so you can ask questions in English, of course, but also in German, so what you feel most comfortable with. Just this presentation was prepared in English. So, yeah, thank you.